So starting test 3 material, we're going to be finding derivatives with the shortcut rules. So we will not have to do it what I would consider the long way, which is finding the difference quotient and then taking the limit of it. So that's what you'll see here on the top. The interpretation doesn't change. So we're still talking about the tangent line slope. We're still talking about instantaneous rate of change. We're still talking about marginal. So there is a little bit of different notation, which is in this first box that you'll see here. Okay, this is what we've been using here. And now they're going to use a slightly different notation because remember, sometimes we won't have something in function form. We may have y equals. So if we have y equals, you're going to put it in dy over dx if x is your variable. Say your variable is a t, then you would put dy over dt. This also tells you to take the derivative of that piece. So if it's a constant, remember what we talked about when we looked at the picture last week, that if we drew a constant function, the derivative of a constant function is 0 because the slope of that tangent line would always be a horizontal line, which would be 0. So just a reminder again, you have your line here that has a 0 slope. So any constant, that is a definition. You need to memorize it. You don't have to derive it anymore. You can automatically tell me that is the answer. So real quick, number 1, if the function is 7, which is a constant, my derivative will be 0. If, number 2, my function is 13, then my derivative is 0. It's super easy to make a mistake on these in the middle, so please be careful. This is just because, again, the slope of the tangent line is horizontal. So we'll always have a 0 slope. Going to our second and probably most important rule for derivatives for a shortcut is what's called the power rule. The power rule says that if I have anything in the form of x to the nth power, and n has to be a real number, so that means it can be negative, it can be positive, then what we will always do is we will bring down the exponent in front as a coefficient and subtract 1 from the exponent. They write it in a slightly different word, but that's how I think of it. You will bring down the exponent as a coefficient and subtract 1 from the remaining exponent. So on number 3, again, make sure you're using the correct notation. Bring down the exponent, subtract 1. So my answer here is 2 to the x power. Sorry, 2 times x. Number 4 is not in the correct format to use the power rule because the power rule says you want it to be in the x to the nth power, but I can rewrite this with a negative exponent. So reminder, good notation. This is not a function form, so it's dy, and I'm taking it with respect to x, so that goes in the denominator. Bring down the exponent, subtract 1. Now, my math lab will accept positive and negative exponents, but for a problem like this, I really would like you to go ahead and rewrite it with a positive exponent, but both of them would be acceptable in my math lab. There will be times that one way is better for us to use than the other, depending on what we're having to do for the problem. So we have a few more problems just using the power rule here. Just showing you it doesn't matter if it's a fraction, a negative exponent, what we have. You may have to rewrite it to be in the correct form. In this case, it's in the correct form, so I'm going to bring down the 4/3, subtract 1. So I should be left with a positive 1/3 power. Number 6. The derivative of here would be, again, there's an exponent of a 1, so we'd bring down the 1, subtract 1. Gives me x to the 0 which is 1. This should make sense. So stop and think about what this would have looked like. This would have been my identity function, which has a slope of 1 everywhere. That's my answer. Going to number 7, we have to rewrite it in exponential form. So square root is the same thing as x to the half power. So again, correct notation, which is really important on this test, dy over dx. Bring down the exponent, subtract 1. So that leaves me with a negative exponent. Again, my math lab would accept that as an answer, but please understand, it's actually a good idea that you understand how I just rewrote that. This would mean bring down the x to the denominator, and 2 is already in the denominator, and x to the half power is the same thing as square root of x. So I'll say that again. Negative exponent means move it down to the denominator, the 2 is already there, and then half power means the same thing as square root of x. So we're going to finish this portion with finishing the constant times a function piece. And so here, I have a number in front. The number doesn't change how we take the derivative. We just keep that and multiply by that exponent I bring down and subtract 1. So a lot of you will skip the steps. I'm going to show it on here. Bring down the exponent, subtract 1. Make sure you're putting that prime in that notation. So it should be 6x squared. Going to number 9, dy over dx. Bring down the exponent, subtract 1. So my derivative is a negative 8x. Notice if it's a polynomial, I'm decreasing the degree by. Rewrite it as 3 times x to the negative 2. Use my correct terminology. Dy over dx. Multiply by the exponent and subtract 1. So I get a negative 6x to the negative 3, which means bring down that exponent. It would at this point accept either one of those pieces. So same idea, but just showing you're going to have to deal with the fraction sometimes. So dy over dx, negative 3/4 times 12, which I can write as 12 over 1, subtract 1. So dy dx, in this case, 4 goes into 12 3 times. I get a negative 9x to the 11th as my answer. You can multiply first, which would have given you negative 36 divided by 4, which would still give you a negative 9. Rewrite number 12, dy dx, bring down the exponent, subtract 1. I prefer the negative 4 over x squared, but my math lab will accept either one of those pieces.